Have you ever been on a roller coaster? To be honest, as an adult, they mostly just hurt. Maybe that's just me being old. But as a kid, I loved them. I would stand in these enormous lines for like a 2-minute ride, right? And the whole time, I would be watching these roller coasters race up and down hills and through loopy-loops. And I always thought, like, what if it just shoots off the rails? Am I sure that it's going to take the same path when I'm on it? Well, it turns out, if you understand the laws of motion and the laws of physics, you can predict the path of a roller coaster. And that's how we design roller coasters, to give just the right amount of fright and excitement, but to always safely bring you back into the station. It all has to do with the laws of motion. And Sir Isaac Newton in the 1600s studied these laws. And that's what we'll take a look at in this unit. Let's take a look at the laws of motion. Let's start by reviewing our lesson objectives. First, we'll introduce Sir Isaac Newton. Then we'll provide an overview of Newton's laws so that you have a basic idea of what each one of these says. And then we'll summarize key ideas needed to understand Newton's laws. We'll dive more into these ideas as we go through our unit. Our modern understanding of motion has everything to do with falling apples. In the 1660s, Isaac Newton saw an apple fall from a tree in an orchard. Why, he wondered, does the apple fall straight down? Why doesn't it float, or go upwards, or even sideways? Isaac connected this motion to the Earth's gravity, and gravity in general to the motion of all the planets in our solar system and beyond. He eventually published his laws of motion and forces in his most important book, Mathematical Principles of Natural Philosophy. In this text, Newton laid out how the regular motions of matter around us can be described by elegant mathematical equations. By merely working out a few problems on paper, we can predict the motion of the stars, of apples, or cannonballs. The universe is a well-ordered, elegant place. Let's take a closer look at Newton and his laws of motion. Let's start with his first law. Strange place to start, right? It says objects don't change their motion without a force. Let me give you an example. The easiest way to see the first law at work is to watch something drifting in space. In space, there's no air and no friction, nothing to slow this craft down. It will continue to drift forever until it comes into contact with something else. Most likely, that would be a star. Here we see another, more terrestrial example of Newton's first law. When you park your car, it just stays there. Not a very exciting application of the law of motion, but it's important. When you go back to the parking lot, to your same spot, your car will still be there. That's what we're saying when we say that an object will continue doing whatever it's doing unless there's a force applied. But sometimes there is a force applied, and that's where Newton's second law comes in. Newton's second law says that force is required for acceleration. Force is basically pushing or pulling on something, and acceleration is changing how quickly something is moving. We'll talk more about those later. Here's an example of Newton's second law in action. Remember, we said that your car just stays still until you put a force on it. Well, this poor guy is having to push his own car. Now he's becoming the force to move it until he can get the car to where it needs it to be. So Newton's second law tells us that a force is required for motion. Newton's third law is often stated that each action causes an equal and opposite reaction. But we can put that into slightly more physicsy language and say each force causes an equal and opposite force. This is the basic principle that allows spacecraft to fly. Notice this space shuttle is pouring out hot gases from explosions in its jet engine behind it. Those hot gases shoot out backwards. And strangely, the shooting out of those particles backwards actually applies a force on the space shuttle to go forward. So every single time you exert a force, there's an equal and opposite force that rises up. More on that later in this unit. Now let's review all of Newton's laws of motion quickly. First, objects don't change their motion without a force. That's the first law. The second law says force is required for acceleration. And the third law says each force causes an equal and opposite force. All right, now we'll review some ideas you need to understand to get Newton's laws. We'll call these key ideas in Newton's laws. The first one is velocity. What is velocity? It's a vector that tells us the rate of change in position. Whoa, that's a lot. Remember, a vector is something with size and direction. So velocity tells us how quickly and in what direction something's changing position. We might call it speed plus a direction. Here we can think about this car's velocity. Its velocity might be 45 miles per hour forward. So it has a magnitude, 45 miles per hour, and a direction, forward. It's also important to understand acceleration. It's a vector that tells us the rate of change in velocity. So again, it has a direction and a magnitude. How quickly it's changing the velocity is its magnitude, and the direction it's changing its velocity is the direction that makes it a vector. Here, for example, we have a top fuel dragster that we saw in Unit 1, and it accelerates really quickly. It goes from sitting still to moving really fast. That's acceleration. A related idea is force, which is a push or pull on an object that can cause motion. It doesn't always cause motion, but it can cause motion. Here's a good example. We looked at this poor gentleman earlier. He's pushing his car. Now, if he doesn't push his car hard enough, it's still a force, but it wouldn't move the truck. So a force is pushing or pulling, and it might cause motion. But if you don't push or pull hard enough, maybe it won't cause motion. All right. The last idea we need to be familiar with to understand Newton's laws are free body diagrams, and we'll spend a whole video talking about these. It's a way to show all the forces acting on an object, a way to show all external forces acting on an object. Let me give you an example. Here we have an anvil hanging on a rope. Any idea what forces might be acting on this? Well, right away, it hopefully is clear that gravity is pulling it down. And because gravity is pulling it down, we know something must be pulling it up. That turns out to be the force from the rope. So this is kind of a rough idea of what a free body diagram looks like. It just maps out the forces on an object. And we'll go through step by step, really slowly, how you can map out all these forces. Okay, now it's your turn to practice. Go ahead, pause the video, and match each term on the left to the correct definition on the right. Then we'll come back and see if you got it right. Okay, first up is force. Force is a push or pull on an object. Next, we have Newton's second law. That tells us that force is required for acceleration. Newton's third law told us that each force causes an equal and opposite force. And lastly, acceleration is a change in velocity. Let's sum up what we've learned. We introduced Sir Isaac Newton. We said he was a really important scientist who lived in the 1600s who developed the laws of motion. We provided an overview of each of the 3 of Newton's laws, and we summarized key ideas needed to understand Newton's laws, like force, acceleration, velocity, and free body diagrams. We'll spend more time diving into each one of these ideas in the remainder of this unit.
Hey, hey.